Welcome to This Explainer. All right, let's just dive right into this. If you've ever gotten a speeding ticket, and let's be honest, a lot of us have, you actually already have a really intimate, real-world understanding of the concept we're unpacking today. Think about it. You didn't get pulled over for where you physically were on the road, right? You got pulled over for how fast you were getting there. Today, we're exploring the mechanics of instantaneous change, the derivative. We're going to look way past the basic math formulas and use this as a profound, dynamic lens for viewing exactly how the systems around you are shifting in real time.
To kick things off, let's ground ourselves in a completely undeniable reality that we've all experienced behind the wheel. Picture this. You're driving a car. How do you actually know how fast you're moving at any given second? You intuitively know that your speed isn't just about your static position on the highway. It's really about how quickly that position is shifting right in that exact, fleeting moment. When we map out a simple drive, the underlying pattern is beautifully clear. As the seconds tick by, the distance steadily grows. You can instantly see that from 0 to 1 to 2 seconds, for every single second that passes, another 10 meters rolls onto the odometer. Our brains automatically process this relationship between time passing and distance covered, and we do it without even breaking a sweat.
And just like that, boom, you naturally calculated a rate of change. You intuitively found the speed, 10 meters per second. By doing that, you successfully answered the crucial question, how fast is this changing right now? You didn't need to write out some complex formula on a chalkboard. Your brain just observed the dynamic relationship between two shifting data points and immediately understood the momentum. Now that exact speed you just calculated in your head, that is exactly what mathematicians formally call the derivative. It's simply a concept that tells us how quickly something is changing. It represents the rate of change of an output, like your distance, with respect to an input, like the time on the clock. The key takeaway here is that it purely measures how fast a quantity is shifting, not the static distance itself. It's all about the motion, not the snapshot.
All right, let's move on to section 2, visualizing the slope.
Imagine a curving line on a graph. At any given point on that curve, the derivative reveals itself as a brilliant visual tool. It's the slope of a tangent line. Basically, a perfectly straight line that just barely grazes the curve at one exact spot. This gives us a really simple way to read the landscape. A positive derivative? That means the function is increasing. You're going uphill. A negative one means it's decreasing. And if the derivative is exactly 0, well, the curve is completely flat right there, typically meaning you've hit a maximum peak or a minimum valley.
Let's apply that visual tool to a standard function, like y equals x squared. Its derivative formula simply becomes 2x. That little bit of algebra acts as a sort of master key for this specific curve. It completely empowers us to find the exact geometric rate of change at any single point along that shape, entirely removing the guesswork.
Check out what happens as x moves further along the graph. Notice how the slope jumps dynamically. When x is 1, the slope is a manageable 2. But step over to an x of 3, and wow, the slope suddenly spikes to 6. The curve gets steeper and steeper. This perfectly illustrates how the derivative tracks the exact rate of geometric change at specific points, capturing that dynamic shifting in real time.
Let's jump into section 3, real-world derivatives.
In physics, these concepts stack on top of each other into a perfect cascade of instantaneous change. You start with your position, measure how fast that position is changing, and you get your velocity. But the cascade doesn't stop there. Measure how rapidly that velocity itself is changing, and you immediately arrive at acceleration. It's a continuous, multi-layered perspective on movement.
And this stacking effect leads us to a much broader application. Engineers and economists use the derivative literally every single day to ask one vital question. If I change the input slightly, how much does the output actually change? They're essentially asking how fast a system is changing right now. It's a profound measure of absolute sensitivity, letting them see how a tiny little tweak on one end ripples all the way through to the other.
This incredible versatility makes the derivative a truly universal language of change, uniting wildly different fields. Whether it's an engineer tuning heater power to control a room's temperature, an astrophysicist tracking the acceleration of a satellite, an economist calculating the marginal cost of a single product, or a biologist modeling population growth, they are all essentially doing the exact same thing. They're using this mathematical master key to measure the fundamental sensitivity of their specific systems. Bringing it all together now, section 4, the big picture. If you take away just one thing from this explainer, let it be this simple underlying contrast. A standard function just tells you, where am I? It's your static position, your total cost, your room's current temperature. But the derivative? The derivative dynamically tells you, how fast am I changing? It is literally the fundamental difference between looking at a static photograph and watching a high-speed video of the world in motion. Across every discipline imaginable, the derivative acts as a universal translator. It completely strips away the specific industry noise and all that complex jargon. Whether you're talking about cost, temperature, or population size, it consistently reveals the pure measurement of change over time. It seamlessly unites all of these completely different metrics under one core, undeniable idea.
In fact, our source material boils this down beautifully to a single, elegant sentence. The derivative is the instantaneous rate of change, the answer to the question, how fast is this changing right now? It really is just that straightforward. It's the mathematical embodiment of the phrase, right now.
So here's the thought I want to leave you with today. The very next time you're analyzing a trend at work, managing your monthly budget, or honestly, just driving your car down the highway, ask yourself, what is the derivative of this moment? When you look at the systems around you today, how fast are they changing right now? Because once you start seeing the world through the lens of the derivative, you stop just seeing where things are and you start seeing exactly where they are going. Thanks so much for joining me on this explainer.